Hey everybody, sorry I'm not there today. I am at the Science Center going to Mars. It's really fun. Anyway, sorry I didn't bring you to Mars, but I've left you with a very capable supply teacher. Not sure who it is, but hello to you. And a bit of a lesson. So you're going to do your lab follow-up today, so dig out your data and stay tuned for my new foray into new technology. Don't worry, I'm not going to set up a YouTube channel anytime soon. We'll see if this works. Now for homework, what you guys had to do was to take the results of the lab procedure that you had done looking at potassium hydroxide and hydrochloric acid. Now your homework was to complete these for your own. What I want you to do today is to consider data as a class collective, and you're going to be determining your delta H values, but then compiling them together. And I'm going to give, I've left a chart so that you can enter these. So these are going to come up in just a moment. But let's take a look at what you needed to do in the questions. So the first thing you had to look at was finding the delta T for your particular three reactions. So in each one of these, you had to record the initial and final temperature. Now I'm going to trust that that worked out quite nicely for you. In part B, it asked you to find the heat produced by the reaction and absorbed by the final solution. So this is simply your Q equals MC delta heat T. Now I want to clarify to make sure that in using the MC delta T that you use the correct value for M. Now based on your assumptions, you should know that C should be the specific heat capacity of water, because we're dealing with aqueous solutions. Your change in temperature would be the final minus initial that you found in each of the three reactions. Your mass, you're looking at the potassium hydroxide. So what you need to think about is in each one, so in reaction 1, you were taking water and dissolving solid potassium hydroxide. So knowing the density of water, you can convert that to grams, adding the mass of KOH. You should have approximately 102 grams. Now, depending on the device that you use, you'll have different decimal places and slight variations. It doesn't really matter. You don't have to have exactly 102, but make sure you use your own value. In reaction number 2, where you took the aqueous solution of hydrochloric acid and you added solid potassium hydroxide, 2 grams of it, you're going to take that same aqueous solution, assuming the density of water, so you'll have 100 grams, plus approximately 2. So your answer should be somewhere around 102. Use your own much more specific and more precise data than just my estimate. And the last reaction, you have 100 milliliters, which was the 250 plus 50. So in this one here, that was your 50 milliliters of KOH plus your 50 milliliters of hydrochloric acid to give you 100 milliliters altogether. With the assumptions that you would use the density of water, you're going to have 100 grams. So those are the three mass values you need to use when you're completing your Q. So now that you have that, you should be able to have a Q value for each one. So you're going to find the Q for each of these. Oops, you can't see my Q. For each of those. So that is part B. Now, in part C, it says they want you to calculate the number of moles for KOH. So that should be as simply as using the mass for the KOH that you had, and then determining your molar mass. So using your periodic table, find the molar mass of potassium, oxygen, and hydrogen, rounding that all together. So you're going to have your molar mass of KOH, and that's going to give you your number of moles of KOH for each of the three situations. So what you need to do next, once you have the number of moles for reaction 1, 2, 3, which may differ a little bit for each one, you're going to take your Q values that you calculated up here, and you're going to divide that by the number of moles of KOH. So you're going to do that for reaction 1, reaction 2, and so on. So those are using your values from B and C. So at this point, what you need to think about is the heat released or absorbed, and in this case you should have had 3 exothermic reactions, will be divided by moles, which gives you a molar enthalpy. Now these delta H's that you're determining should be based on being exothermic. You're going to decide, are they positive or negative? Now, if I was there, I'd actually ask the question, so, is it positive or negative? And right now, you're all putting up your hands, I'm sure, and waving at the supply teacher. Which is it? Right, if it's exothermic, we're going to have negative values. All right, so I'm going to get the video to be stopped just for a moment. And I would like you guys to take a moment to calculate your three values. So your delta H for the first reaction, the delta H for the second, and the delta H for the third reaction. We're going to take all three of these values, and you're going to include your uncertainties because you are good lab students. Double checking that you use the same mass that I mentioned right up here. And I want you to check your calculations with your classmates. So once you have that done, I'm going to ask that the supply teacher now brings out this form that I just left, and that you come up and you add your results in here. So we probably have about 10 groups. Those of you who were away last week can actually use someone else's data or just these class results, all right? It'd be good for you to use the raw data to get used to doing the calculations, but what we're going to do is we're going to have the three different values, and we're going to average them, all right? So you're going to average these values, and those are the ones that will give us the values that we want to use in our final portion. Now remember, if there's ones that are way out to lunch, we'll consider those outliers. Don't make the people feel bad because, you know, sources of error happen, but that way we can have good values for the rest of our calculations. Okay, so I'm going to pause now, do your calculations, and enter your results onto the page that the supply teacher has for you. So if you've done your calculations, you should have averaged them, and I'm going to guess you have values similar to what I have here. Now, when you look at these values, and of course yours may be different because of our class values, but what we're looking for is we're looking for a pattern. So hopefully your data is similar enough that you can sort of see the patterns that are arising here. So when we look at these values, and these are ones I've had in past classes, so approximate values for each of the reactions. What you needed to do in one of the earlier questions, or actually question number 3, you had to do the net ionic equations for these three reactions. So what you did in the first one is you took KOH and you dissolved it. So you ended up with the the potassium ion and the hydroxide ion, and then the H that you saw here. So in this case, that was reaction 1. It produced 35 kilojoules. Now, this is negative, so make sure we put our negative values in. In reaction 2, you took solid KOH and in an aqueous solution of hydrogen. So if you do the net ionic equations, and if you don't remember how to do this, there is a sheet on my website on D2L that you can look at to review it, or get one of your classmates to review that. We've canceled all the spectride ions just using the ones that are involved. So it's the hydrogen ion that is involved here, leave me with water, and the potassium ion. Now in this case, this gave off about 80 kilojoules. Again, exothermic's a negative here, but we simply add it in there. In reaction number 3, this one were the two dilute solutions, and in the neutralization, essentially all that's happening, if you remember your acids and base study, is you're taking the hydroxide ion from the potassium hydroxide, the hydrogen ion from the hydrochloric acid, they neutralize by forming water. So these are the only real ions that we're worried about, and in that reaction, we produce 50 kilojoules approximately. Again, your values will be slightly different. There, we need to think about what the relationship is between these three reactions. So thinking about this right now, I just want to pause for a second for you to consider how are these three connected. So talk with your partner, someone next to you, the people behind you. What is the relationship between these three? All right, welcome back. So in looking at our three equations, what we need to consider is how the three equations relate to each other and figure out what their relationship is. So we have 35 kilojoules in reaction 1 released, 80 in number 2, and 50 in number 3. Now if you look closely, what you can actually see mathematically is that the heat reaction of number 1 plus the heat reaction of number 3 actually add up, and I'm going to use the approximately equal to number 2. Now, this is not just true mathematically. I want you to take a look at the actual equations themselves. So we can actually add up number 1 and 3, adding those together, and you'll find, using what you know about net-on equations and adding together, what we have is, if we add these two together, we get, so reaction 1, we have KOH here. We are going to have OH, it's a -1, and we have that one. So I've used up all the reactants and put them on the one side. Now, on the product side, I'll have K positive plus OH to the -1 here and here, and then I also have water. So in looking at this, what you're going to find in this particular situation is we have KOH on this side, water over here. My two hydroxides actually cancel out, and because they're on both sides, so I can cancel them, leaving me with KOH solid plus H plus aqueous, leaving potassium ion aqueous and H2O. And if you look, here we go, I have exactly reaction number 2. Boy, is that messy. So we actually have a summative relationship, not just in the heat values, but also in the ions and compounds that are involved. So we actually can find reaction number 2 by combining this. So think about it qualitatively as well. We took a solid KOH and dissolved it, which is happening here too, because the solid KOH is dissolving in the water that's part of the solution of the hydrochloric acid. Here, this one we took the KOH and the HCl and neutralized them. So the combination of 1 and 2 actually gives you the same sum effect as number 2. Sorry, 1 and 3 give you number 2. So we could have just gone to number 2 to find out the combined effect. So this is almost like a two-step process. Together, they are number 2. And mathematically, you can see this as well. This is what we call Hess's law. So essentially, in enthalpy changes, if a set of reactions occurs in a different steps or a different order, but the initial products and the final products are exactly all the same, the overall enthalpy is the same. This is something we know of as Hess's law. Sorry, and it's a little too far away. Let me just back it up a little bit here so you can see it better. There we go. So Hess's law. You have 2 or more equations and you know their enthalpy. If you can add them up together, that produces what we call a target equation. If that is the case, as it was in our lab with the equations or reactions number 1 and 3, we can also add up their enthalpies to give a total heat of reaction. So Hess's law says this: the value of the enthalpy for any reaction can be written in steps that equal the sum of the values of the delta H for each of the individual steps. So here it is. Essentially, the target equation, which in our case was reaction number 2, is the sum of all the other enthalpies. It can be 2 steps, it could be multiple steps. So we think of it simply as the sum of the delta H's that we know. So in essence, we didn't even have to do reaction number 2 at all. We could have simply done 1 and 3, which gives us the same net outcome as 1 and 3 done. And our values, hopefully your experimental values, show this a little bit as well. Now you have your own note paper right now. I would like you to take a look at this handout once it's distributed to you. Also, your textbook explains Hess's law quite nicely. In just a moment, I'm going to go through some examples with you of Hess's law. But essentially what happens, it allows us to figure out enthalpy changes in reaction without actually doing the calorimetry. So if we have the individual steps and we know the enthalpy for different types of reactions, we can actually use that to find out a target reaction. So take a moment to consider the guidelines we use with Hess's law. 1, if you reverse an equation, the signs of delta H will change. So we've already seen that when we talked about the law of conservation of energy, in that for example, if you create water, you get 1 enthalpy. If you take it apart, the value is the same, but it's the opposite sign. So we're going to use that guideline. The second one, we want to think about the coefficients, or those molar ratios in the equation. If you multiply the whole equation out by 2 or divide it by 2, you're going to be doing the same manipulation with your delta H. So if you want to change your values by dividing in half, your enthalpy will also be in half. I'm going to pause now. I'd like you to get out your worksheet. There are some examples there for you. We're going to work through those together.